classes we have started new lesson, that is solid state electronics or semiconductor electronics. In that we have completed some concepts. In the first class we have completed introduction part. So introduction means what is electronics, what are electronic devices, and what is semiconductor electronics, what are the building blocks of the electronic circuits, and also how we can classify materials based on conductivity, that is conductors, insulators and semiconductors. And in next class we discussed about band theory, energy band theory or band theory. In that band theory we have discussed what is a valency band, conduction band and a forbidden energy gap. And based on band theory, how we can classify solids into conductor, insulator and semiconductor. And we compared all these three, we compared with around 5 to 6 points. And next class we discussed about semiconductors. What are semiconductors? What are the types of semiconductors? That is elemental and compound. Again, in compound semiconductors we have inorganic, organic and also polymer type. And also we discussed about intrinsic and extrinsic semiconductors. That intrinsic semiconductors concept in the previous class I have discussed. What are intrinsic semiconductors and their properties, and also what are the advantages and what are the disadvantages, and how conductivity depends on what factor. All these concepts we discussed. And also bond structure and band structure both we discussed with one germanium taken, and how electrons will be shared by the germanium with the neighboring atoms also we discussed. And now we have started extrinsic semiconductors. In that extrinsic semiconductors I have given two types. One is N-type semiconductor and one is P-type semiconductor. And also I mentioned about a doping concept also. In the notes already I think I have written doping, process of adding impurities to the pure semiconductor is called as doping. What is the purpose of the doping? Generally, without heating the material, just by doping a material with a suitable proper impurities, conductivity will be increased. To increase the current flowing through the semiconductor or to increase the conductivity, so there is a need of doping. So at the time of the doping, generally for doping, what type of atoms we have to choose? There are some properties. One is the size of the dopant atom or doped atom should be comparable to the size of the semiconductor atom. If you want to dope one dopant atom with germanium, size of the germanium atom and the size of the doping atom both must be nearly equal. One property. And one more, whatever the atom we want to dope or whatever the impure atom we want to add to the germanium, it should replace one of the semiconductor atoms. For example, semiconductor contains 100 atoms. We are adding one atom to the germanium. So this atom should occupy one of the position of the germanium atoms. At a particular place it should occupy. That is one property. And one more, the dopant atoms should be proper. Proper means we should not add bundles of the atoms. For every 10 to the power of 8 atoms, only should add one atom. So that conductivity nearly 1000 times increases. For example, germanium contains 10 to the power of 8 atoms. If you want to get a more conductivity, how many atoms you should add means no need of much atoms, only one atom is sufficient. So there are the properties of the dopant atoms or dopant impurities. And one more, what are the types of the dopants we want to select for germanium or silicon? Generally, germanium or silicon is a tetravalent. They contain 4 electrons in the outermost orbit, valence shell. So that's why we have to choose either trivalent or pentavalent. So germanium generally tetravalent, 4 valence electrons. If you are choosing a 5 valence electrons atom, that is called pentavalent, just one above. And if you want to choose one below means that is trivalent, 3 valence electrons. So that's why we can choose either trivalent or pentavalent. So example for a trivalent means one simple short form also I have given: baggit, boron, aluminium, gallium, indium, thallium. So this type of any atom you may choose. So we can dope to the pure semiconductor. Then the semiconductor may be converted into positive type or P type. And we can choose pentavalent also. Pentavalent means PASB, one short form given. PASB means phosphorus. arsenic, antimony, and bismuth. So this type of atoms we can choose. They are pentavalent. Whenever this type of atoms added to the pure semiconductor, so that will be converted into N-type semiconductor or negative type semiconductor. So we can choose two type of dopants. One is trivalent, one is pentavalent. But how we can add? So simply, if you take one germanium crystal, if take one dopant atom, maybe trivalent or pentavalent, if you just kept on the surface of the germanium, so that's not called doping. Correct? Means what we have to do means, it is a, for example, it is a germanium crystal. It is a dopant atom, maybe boron or arsenic something. After placing the atom like this, we have to heat the sample. Whenever it is heated to high temperature, so that will be converted into molten state, liquid state. Then this atom will be penetrated into the germanium crystal. After cooling, what will be happen? Both will be mixed. We cannot separate the impure atom other side. That's why by the method of diffusion, one method is called diffusion. So means placing the given sample like trivalent or pentavalent on the germanium or silicon, and by heating a suitable temperature, and then we have to cool. Then automatically it will be converted into extrinsic semiconductor. So one method. Or by bombardment. So we have to take a germanium or silicon target here, and whatever the atom we want to dope, that we have to send with a high speed. Whenever it is moving with very high speed, it will penetrate, collide and penetrate it into the sample, and so that is also one method, by bombardment of the particles, or maybe by heating, or by diffusion method. So by using a suitable methods only we can dope. That is a doping. Now depending upon the doping, we have two type of extrinsic semiconductors. One is N-type semiconductor. N-type semiconductor. N-type means a negative type. N-type semiconductor. Here N-type means a negative type. So generally, what is a N-type negative N-type semiconductor means, to an intrinsic semiconductor, that is a pure semiconductor. Whenever pentavalent impurities are added to a pure semiconductor, when pentavalent impurities are added, then the obtained semiconductor is called N-type semiconductor. To a pure semiconductor, when pentavalent impurities are added, then the obtained semiconductor is called N-type semiconductor. So we have to choose either germanium or silicon. Then we should add the pentavalent atoms, pentavalent dopant atoms. Then we are getting some semiconductor. So that can be called as N-type semiconductor. So to a pure semiconductor, when pentavalent impurities are added, then the obtained semiconductor is called as N-type semiconductor. Here N-type means negative type, because more number of electrons are present comparing to positive charges. So here what type of dopants we are adding? Pentavalent impurities. Example for pentavalent impurities we can write arsenic or phosphorus, arsenic, antimony, bismuth. So generally we are writing this one as POSB, short form like this. So these are generally having 5 valence electrons. So pentavalent atoms are having 5 valence electrons in the outermost orbit. They are having 5 electrons. They are having 5 valence electrons. So to the pure semiconductor, when we are doping with this type of pentavalent atoms, that will be converted into one N-type semiconductor. And here example, phosphorus, arsenic, antimony, bismuth in the outermost orbit, they contain 5 electrons or 5 valence electrons. whereas the germanium or silicon is trivalent, tetravalent, 4 valence electrons. So actually germanium or silicon is tetravalent. Tetravalent, that means it contains 4 valence electrons. Now how we can take a bond structure means I'll take one germanium or silicon atoms like this. So these are germanium atoms. One crystal I am choosing, germanium crystal, which contains germanium atoms. In the outermost orbit they contain 4 electrons. So that is a tetravalent, it is. But middle I am choosing any one sample, any one pentavalent atom which is nothing but arsenic. Observe the diagram carefully. But remaining all, I have selected germanium, 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 and all germanium except middle I have selected one arsenic atom. So because of the doping, so this arsenic atom will replace one of the germanium atom and it is occupying in this place. But generally all the germanium atoms contains how many electrons? 4 electrons in the outermost orbit like this. So germanium is a tetravalent, so it contains 4 electrons in the outermost orbit or 4 valence electrons like this. But generally semiconductor has what type of bonds means covalent bonds. It can share with the neighboring electrons, it form the bonds with the neighboring electrons. So here we are choosing all the germanium atoms with the 4 electrons like this. But the arsenic is a pentavalent, that's why it contains 5 electrons. Instead of the 4, it only contains 5 electrons. But how the bonds will be formed by the arsenic with the remaining germanium atoms, we have to check. So here, remaining all the germanium atoms I have given 4 electrons only. But the middle arsenic is a pentavalent, means 5 electrons. 4 I have shown here, extra electron I am showing in this place. So that is the 5th electron. I am showing a 5th electron. Now all the germanium atoms are forming with the bonds with the neighboring germanium atoms like this, electrons. You can choose like this. The formation of the bonds by the germanium with the neighboring germanium atoms. Generally if you take at a room temperature or maybe at a lower temperature also, we can choose the bond structure like this. It is a bond structure of the germanium after doping with the pentavalent atom like arsenic. Now check. All the bonds are completed. So if you observe carefully, all the germanium atoms are forming the bonds with the neighboring germanium atoms. So middle we are doping with one arsenic atom which contains 5 electrons. But out of the 5 electrons, how many electrons participated in the bond? 4 electrons only, because nothing but germanium is a 4, correct? Germanium or is equal to arsenic, for example, having a 5 valence electrons, but germanium having only tetravalent 4 electrons. Out of the 5 electrons of the arsenic, 4 electrons can complete the bonds with 4 germanium atoms, but 1 extra electron is there. So this extra electron is donated by arsenic atom. That electron is nothing but no bondage. No bond means automatically it is a free electron, so which causes conduction. So whenever we doped with one arsenic atom to the germanium or silicon, so arsenic contains 5 electrons and germanium atom contain 4 electrons. Out of the 5 electrons of the arsenic, 4 electrons can form the bond with the neighboring electrons of the germanium atoms. But 1 extra electron was donated by arsenic atom, so that electron is a free electron or a conduction electron which causes current. For example, I doped with 2 arsenic atoms, what will be happen? 2 arsenic atoms means 2 electrons will be donated. 10 atoms I doped, then 10 electrons will be donated. So number of atoms doped will be equal to the number of free electrons here. Correct? Means for every atom we are going to dope with germanium or silicon, so that pentavalent atom can donate 1 electron. Almost both are equal. So at at lower temperature, but at a higher temperature, what will be happened? So this electron is nothing but called free electron. It is a free electron which causes electric current. Correct? It is a free electron. So for example, I am taking a band structure like this. Maybe at a very low temperature, you may select. So this will be, lower part will be Valency band. So this is called Valency band, and this upper part can be called as conduction band. So it is called conduction band, and the lower part is a Valency band, and the middle can be called as forbidden energy gap. So in case of the germanium, what is the forbidden energy gap? So this forbidden energy gap will be equal to 0.7 electron volt. 0.7 electron volt. So Valency band contains electrons. Valency band having electrons. But just imagine, I doped only one atom. Whenever I doped one atom, means how many electrons donated? Only 1 electron donated. If I doped 4 atoms, then 4 electrons will be donated. But where this all the 4 electrons will occupy? At a very low temperature. Just imagine, at a very low temperature. So the Valency band is full of electrons, but a conduction band nil, no electrons. That's why no current also passes. But I doped with 4 atoms. Then what will be? Or 5 atoms I doped. Then what will be happen? Each and every arsenic atom can donate 1 electron, means 5 atoms if you dope, there will be 5 electrons. But where this 5 electrons will be present? Not in the conduction band, not in the Valency band. They will occupy a separate energy level just below the conduction band. Just below the conduction band, they will occupy here. If you dope, for example, 5 atoms means 5 electrons. If you dope with 6 atoms means 6 electrons. So here one layer will be formed like this. So this layer is called donor energy level. That level can be called donor energy level or Fermi energy level. So it is also called a donor energy level or Fermi energy level. Fermi, F-E-R-M-I, Fermi energy level or donor energy level. Why we are calling this donor? All the pentavalent atoms are able to donate the electrons for the conduction. That's why that atoms are called donor atoms. And the level, whatever the electrons occupied here, just below the conduction band, so that level can be called as a donor energy level. And here, where it is occupied or where it is present? Bottom of the conduction band, just below the bottom of the conduction band. It is for example, the line is the bottom of the conduction band. It is just below the bottom of the conduction band. Between these two, there is a small energy gap, that is only 0.01 electron volt, very less value. But actually this total gap, how much? Between the Valency band and the conduction band, gap is 0.7 electron volt for germanium. For silicon, 1.1 electron volt. But here below the bottom of the conduction band, there is a donor energy level. Between the donor energy level and the bottom of the conduction band, also there is a small energy gap that will be equal to 0.01 electron volt. So here this energy value will be Eg dash, we can write 0.01 electron volt, very less value, very less value. So that's why easily electrons, these electrons can jump to the conduction band. Even if you are giving a very little bit amount of energy, 0.01 if you are giving, means easily they can jump to the conduction band, which causes electric current. For example, at a room temperature, what will be happened? At room temperature, what happened means sum of electrons from the Valency band may jump to the conduction band like this. Whenever one electron jumps from the Valency band to conduction band, it will leave one hole. Correct? The deficiency of electron is called hole. But at a very low temperature, Valency band is having electrons, but a conduction band no electrons. But donor energy level will be just below the conduction band. but at room temperature or at a higher temperature, some of electrons in the valency band will gain energy, they can jump to the conduction band. For example, two electrons jump from the valency band to conduction band, then what will happen? There are two holes. If three electrons jumps, there are three holes you should take. For example, three electrons jumps from the valency band to conduction band. So how many holes means here? There are three holes. Now, as a result, finally, how many electrons are present in the case of N-type semiconductor and how many holes? Which are majority, which are minority? Check carefully. For example, 1, 2, 3, 4, 5, 6 atoms I doped, arsenic atoms. How many electrons here donated? 6 electrons. So 6 electron, example only, 6 electrons donated by arsenic atoms. Plus, at a room temperature, sum of electrons jump to the conduction band. How many? 1, 2, 3. So it is equal, I am writing 3 electrons. Total 9 electrons are present in case of germanium after doping. Just example only. No need to remember the numbers. But how many holes are present? 1, 2, 3. Here, because of this donated electrons, no holes. Only electrons jumps from the valency band to conduction band means 3 holes also created. So there are 3 holes. Now finally check which are majority, which are minority. Electrons 9, but holes 3. Correct? That means number of electrons are more than number of holes. So clearly how to remember? Number of electrons in the N-type semiconductor are greater than number of holes. So generally electron is having what type of charge? Negative charge. So more number of electrons means more negative charges. So here less number of holes means less positive charges. More number of electrons indicates a more negative charge. That's why the semiconductor is called negative type semiconductor. So short form we are writing as N-type. If it is for example more number of positive charges are there, what we should call? Positive type semiconductor, which is called P-type semiconductor. So here number of electrons are more than number of holes you should write. It is a band structure, and how current passes means whenever some temperature it is connected to the battery, after reaching a certain voltage, electrons easily transferred from the valency band to conduction band and they causes electric current. So your current is due to only electrons, only holes, or due to both? Both. 9 electrons are there, 3 holes are there. So current is due to both electrons and also holes. But which current is more? 9 electrons means current due to electrons more than current due to holes. So here number of electrons greater than number of holes. Current due to electrons greater than current due to holes. But what is the total current means? I is equal to IE plus IH we can write total current. Correct? IE equal to IE plus IH. So don't write. It is a bond structure. It is a band structure. You should write. Correct? That's about N-type semiconductor. So briefly I will give again. If you are unable to write notes, so write important points. So here what you should write this one? Definition: to a pure semiconductor, when pentavalent impurities are added, then the obtained semiconductor is called as N-type semiconductor. And generally here pentavalent impurities are used here, are added to the semiconductor. Example for pentavalent semiconductors, dopants: phosphorus, arsenic, antimony, and bismuth. So for example, to remember short form, PASB. So PASB means PA, first P indicates phosphorus, AS indicates arsenic, SB indicates antimony, and BI indicates bismuth. Correct. Now here these are having 5 valence electrons. Pentavalent atoms are having 5 valence electrons, but germanium or silicon is tetravalent. It contains 4 valence electrons. Now we can write pentavalent impurities are also called donor atoms. Pentavalent impurity atoms are also called donor atoms. Since why they are called donor atoms means sorry, since they donate since they donate conduction electrons, since they donate conduction electrons, they donate means every pentavalent atom which we are doping can donate only one electron. So number of atoms increases means number of electrons also increases, correct? Now, so here electrons are majority charge carriers. Here electrons are majority charge carriers and holes are minority charge carriers. Electrons are majority charge carriers and holes are minority charge carriers. Minority charge carriers. Here we can write Ne greater than NH. Ne greater than NH. Number of electrons are greater than number of holes. Next one more. Current due to electrons. Current due to electrons is greater than current due to holes. Current due to electrons is greater than current due to holes. Current due to electrons is greater than current due to holes. But total current I is equal to total current I is equal to IE plus IH. Total current I is equal to IE plus IH. But majority IE, but minority IH should take. For example, if you multiply Ne into NH, what you will get? Ne into NH is equal to, generally in the last class also mentioned, Ne number of electrons in the conduction band, NH number of holes in the valency band, Ni means intrinsic charge carriers, which are also called either electrons or holes. If you multiply both means Ne place I can write Ni, NH place also I write Ni, Ni into Ni square we can write, Ni into Ni is equal Ni square we can write, correct? Ne is equal Ni, NH also Ni into Ni is equal Ni square. Write this formula important for competitive exams. So Ne into NH is equal to Ni square. Next, in N-type semiconductor, the electrons donated by, in N-type semiconductor, the electrons donated by pentavalent dopants, the electrons donated by pentavalent dopants will occupy a separate energy level, just below the bottom of conduction band, which is called, one name also have given, just below the bottom of conduction band, which is also called donor energy level. That level is called donor energy level. Competitive exams, 3 questions important. So what is the position of the donor energy level? Where it will occupy will be asked. Donor energy level. How much energy gap here means only 0.01. Where to where this gap? Donor energy level to the bottom of the conduction band. This energy gap will be only 0.01 electron volt. That's only 0.01 electron volt. Next, to a pure semi to a neutral it is important point, to a neutral germanium crystal, germanium or silicon, to a neutral germanium or silicon, simply write short form GE or SI, to a neutral germanium or silicon crystal, we are doping with a neutral pentavalent atom, a neutral pentavalent atom. Hence, the net charge, hence the net charge or net current, anyone. Hence the net charge of N-type semiconductor is 0. Hence the net charge or net current or net electrical conductivity, all meaning same. Hence the net charge of N-type semiconductor is 0. It is very important. Here, for example, a germanium having, for example, number of atoms like 1, 2, 3, 4, 5, 6 atoms are there. These are the germanium atoms. But each and every germanium atom contain equal number of electrons and protons. For example, if you take carbon, it contains 6 protons, 6 electrons. Both will be cancelled. Net charge equal to how much? 0. If you take oxygen, atomic number 8, it contains 8 protons, 8 electrons. Both are equal and opposite. Both will be cancelled. 0. If you take a germanium, also each and every atom contain equal number of electrons and protons. That's why net charge is equal to 0. Now I am going to add one arsenic atom. Then what will be happened? Arsenic atom also having a same number of electrons and holes in its inside. That's why arsenic atom also neutral. To a total germanium is a neutral. We are also adding one neutral atom. Then finally what happens to the net charge? 0. Also it is a neutral only. So N-type semiconductor is electrically neutral. So in bracket if you want, write there only. Net charge is 0. That in bracket write. That is, it is electrically neutral. N-type semiconductor is no charge and no current also, net current also flows. It is a purely electrically neutral. Theory question important. Generally may have number of electrons more, number of holes less, like that. Based on that you can choose generally answer. It is a charged but not charged. So initially before doping it is a neutral. We are also doping one more neutral atom. To the neutral germanium, if you add one neutral atom, nothing will be happened. The total will be also electrically neutral. So that is about N-type semiconductor. And if you want, you may draw this one rough diagram, and here also band structure also may draw rough diagram both. That's about N-type semiconductor. In N-type semiconductor, if you connect one cell or battery to the N-type semiconductor, all the electrons are moving towards the positive terminal of the battery, but the holes are moving opposite to the positive polarity of the battery. So the current is due to both electrons and also holes, but a majority electrons and minority holes. That's about N-type semiconductor. Next we'll go for second one, P-type. Second extrinsic semiconductor, which is called P-type semiconductor. Here P-type indicates a positive type. So almost structure will be like this only, but little bit variation. So here we should take, instead of the pentavalent, what type of atoms we have to choose? Trivalent, like a boron, aluminum, gallium, indium, thallium, the type of you have to choose. So I am choosing one boron atom or indium, your choice. B, I am writing a boron. But the boron contains only, trivalent means 3 electrons instead of the 5, 3 electrons. So you should take a 3 electrons only, but there will be one vacancy. So the bond is not completed one. So 3 bonds completed, but 1 bond will be vacant. So you can draw the structure like this. In case of the p-type semiconductor, the structure of the p-type semiconductor will be like this. So your choice, any one trivalent atom you can choose, either boron, aluminum, gallium, indium or thallium, the type of any trivalent atom we can choose. But there will be one vacancy, should take here. There will be one vacancy. So how we can write definition for a p-type semiconductor? In the previous, whatever the points you have written, there will be just a modification you should write. What is a p-type semiconductor means? Similar type of definition you should write. To a pure semiconductor, when trivalent impurities are added, to a pure semiconductor when trivalent impurities are added, then the obtained semiconductor is called, to a pure semiconductor when trivalent impurities are added, then the obtained semiconductor is called, p-type semiconductor. Obtained semiconductor is called p-type semiconductor. That is simple definition for a p-type semiconductor. So we have to choose either germanium or silicon, a pure semiconductor, which is also called intrinsic semiconductor. So to this pure semiconductor, whenever we doped trivalent atoms like a boron, aluminum, gallium, indium, thallium, so then automatically the pure semiconductor converted into one extrinsic type semiconductor, which is called a p-type semiconductor. So here we have to use what type of atoms means trivalent atoms. So trivalent impurities are doped to the pure semiconductor. But example for trivalent impurities means we can write a short form I have given already. Baggit means a boron, comma aluminum, comma gallium, comma indium, and thallium. So this we can write a short form Baggit. But the exam don't write. So only to remember easily, short form Baggit. like a boron, aluminum, gallium, indium, thallium, they are nothing but trivalent. So they are trivalent means they are having 3 valence electrons. So in the outermost orbit they are having 3 electrons. So they are trivalent, 3 valence electrons. But whatever the pure semiconductor we have chosen, that is either germanium or silicon, it is a tetravalent. So it contains 4 valence electrons. Germanium or silicon is having 4 valence electrons. They are tetravalent. Then how the bonds will be formed if you observe carefully? Germanium contain 4 electrons. Germanium 4 electrons in the outermost orbit, whereas a boron contains only 3 electrons. So 3 electrons of the boron are formed the bonds with the 3 electrons of the germanium. But 1 electron in the germanium always try to complete the bond. So try to complete the bond means it will always try to accept 1 electron. So that's why here whatever vacancy is there, that act like one hole. So here also one hole will be created. The deficiency can be called as one vacancy, which is called one hole. When for every boron atom or maybe trivalent atom we are doping, what will be happen? One hole will be created, one excess hole. If you are adding, for example, 2 boron atoms, then 2 holes. 10 atoms, 10 holes. So as the number of atoms doped increases, the number of holes also increases. Why it is called hole means this vacancy always try to accept 1 electron from the neighboring bond to complete the covalent bond. That's why that can be called as acceptor impurities. But whereas pentavalent atoms are called donor. So they are donating 1 electron, but these are accepting 1 electron. That's why we can write here. Trivalent impurities are also called acceptor dopants or acceptor atoms. They are also called acceptor dopants. So this can be called as a hole. But here what type of charge carriers are more? Holes more or electrons more? Means if take the band structure like this, the lower part can be called as a valency band and upper part can be called as a conduction band. So this is a conduction band and this lower part can be called a valency band. For example, at a very lower temperature, so not at room temperature, also very low temperature I observed, so it contains electrons. For example, it is having like 8 electrons are present here. So total there are 8 electrons present in the valency band, but a conduction band no electrons, 0 electrons, correct? So before doping also we can observe like this. But after I doped with one atom, one boron atom, one excess hole will be created. But where the hole will present? In the previous case, whatever the electrons are donated by arsenic, they will occupy one layer just below the bottom of the conduction band. But here where the holes will be occupied means just above the upper layer of the valency band. So for example, 10 atoms I doped, then 10 holes will be created. 5 atoms are doped, 5 holes will be created. All these holes will occupy a separate layer just above the valency band like this. The holes will occupy a separate layer just above the top of the valency band like this. So this layer can be called as acceptor energy level. Acceptor energy level. So here the gap between, energy gap between the top of the valency band and acceptor energy level also equal to this value 0.01 electron volt, very less value. So generally this will be forbidden energy gap. For germanium, that value 0.7 electron volt, that value same only. For example, at room temperature what will be happened? At room temperature the electrons in the valency band can absorb some amount of energy, they may jump from the valency band to conduction band. If one electron jumps here, for example, check here, what will be happen here? Vacancy of electron will produce one hole. There one hole will be created. So this electron also jumps from the valency band to conduction band. So here one more hole will be created. Correct? Now check here. Finally, number of electrons more or number of holes more means in the valency band there are 2 electrons. And also here 1, 2, 3, 4, 5, 6, 7, 8 holes also there. So total there will be 10 holes. But number of electrons here 1, 2. So that's why in case of the p-type semiconductor, number of holes are greater than number of electrons. Current due to holes are greater than current due to electrons. That you should write. So you can write next point. In a p-type semiconductor, holes are majority charge carriers. Holes are majority charge carriers. Holes are majority charge carriers. And electrons are minority charge carriers. Holes are majority charge carriers and electrons are minority charge carriers. So in short way we can write like this. NH greater than Ne means the number of holes are greater than number of electrons. Sentence form means number of holes are greater than number of electrons. Similar way, current also, current due to holes greater than current due to electrons. Number of holes are greater than number of electrons and current due to holes is greater than current due to electrons. Current due to holes is greater than current due to electrons. But what is the total current? Adding both. I is equal to IE plus IH. Total current I is equal to IE plus IH. I is equal to IE plus IH. Here also you have to understand one important thing. To the neutral germanium crystal, we are adding or we are doping one neutral boron atom. Finally, what is the condition of the p-type semiconductor? Neutral, electrically neutral. So that also right, last point. To a neutral germanium or silicon crystal, to a neutral germanium or silicon crystal, we are doping with a neutral trivalent atom. We are doping with a neutral trivalent atom. Neutral trivalent atom. Hence, a p-type semiconductor is electrically neutral. A p-type semiconductor is electrically neutral. That's important point. N-type semiconductor also electrically neutral. P-type semiconductor also electrically neutral. So sometimes in an exam they may ask distinguish between p-type semiconductor and n-type semiconductor. The differences will be asked. One important 5 marks question, or sometimes 3 marks may be asked. 3 marks or 5 marks question. So we should write the differences. How we can write difference means, so we write a box type only. Write one side write n-type semiconductor. One side write n-type semiconductor, and one side write p-type semiconductor. One side write n-type semiconductor and other side write p-type semiconductor. At least if a 3 marks question means you should write 3 points, or 5 marks question means you should write 5 points. one side may put the heading N-type semiconductor. So left side may write definition, and right side also we can write definition. N-type semiconductor, and the right side it is a P-type semiconductor. N-type semiconductor, P-type semiconductor. First point, right, definition. It is obtained. It is obtained. It is obtained by doping. It is obtained by doping a pure semiconductor with. It is obtained by doping a pure semiconductor with pentavalent impurities. Pentavalent impurities. It is obtained by doping a pure semiconductor with the pentavalent impurities. Pentavalent impurities. So right side same definition statement you should write, but small change. Pentavalent place you should write trivalent. One word only how to change right side. It is obtained. It is obtained by doping a pure semiconductor. It is obtained by doping a pure semiconductor with trivalent impurities. Trivalent impurities. Trivalent impurities. Here the dopants are called. Here the dopants are called donor atoms. The dopants are called donor atoms or donor dopants, donor atoms. But here the dopants are called acceptor atoms. Here the dopants are called acceptor atoms or acceptor dopants. Here electrons are majority charge carriers. Electrons are majority charge carriers. Right side holes are majority charge carriers. Electrons are majority charge carriers here, and right side holes are majority charge carriers. And one more, current due to electrons greater than current due to holes. Current due to electrons greater than current due to holes. Current due to electrons greater than current due to holes. But right side should write opposite. Current due to holes greater than current due to electrons. Fifth point you can write about donor energy level. Donor energy level is just below. Donor energy level is just below the conduction band. Just below the conduction band. But right side what you should write? Acceptor energy level is just above the valency band. Acceptor energy level is just above the valency band. Just above the valency band. So it is about P-type and N-type semiconductors and the complete concept. So completed this part. And tomorrow, next class, I'll give some important formulae. So regarding N-type and P-type semiconductor, and not useful for PUC, but NEET or JEE level compulsory they're asking questions. NEET, JEE or KSET, so compulsory numericals will be asked. So tomorrow I'll give some important formulae. Okay, thank you.